Hi everyone, my name is Kathy, and this is a set of videos that I've wanted to make for quite a while, and it is on analysis. So this part of the course is probably a little bit new for most of the students who are taking this course. It's something that's different from everything else you've done before. So I thought that this would actually be one of the sections that I really should make a video on. So let's start by talking about what analysis is. So this first video is going to be a brief introduction to analysis, what we're really looking for, and then in the later videos, I'm going to show you like the mechanics of how to actually do it. So this is the intro video, sort of like giving you the overview. So the first I want to talk about is what do we mean by analysis of algorithms, okay? So when we talk about analysis of algorithms, what we're really talking about is we're trying to measure resource consumption of a function, okay? How much resources will a function or a program use when it's running? Okay, that's really what we're talking about. Now, when we're doing analysis, we're doing a very theoretical type of analysis. So this is not like actual. And actual, sometimes things like hardware and so on is actually going to come into play, and it's actually going to have some effect on real life situations. But what we're talking about in this part is what the expected thing is, and then how that works out. Like, how can we expect a function to perform, for example? So that's where we're going to begin. Okay. Now, analysis starts by looking at, as I say, resource consumption. So we should first of all define what resources mean. What are resources? So resources are basically anything that is limited on your computer. Now, in general, this course will be looking at two things and mostly really one thing, mostly about time, but there's also memory involved. Okay, so those are the two main resources that we always look at. Time, because we're always we always want to consider how fast our program will run, so time, and memory because we have limited memory. Uh, Whether you like, I know that nowadays we have like, the standard spec is like 32 gigs of RAM and whatnot. So it's not, but there's still some constraint, especially given the amount of data that we're expected to process. So resources is really boils down to typically time and memory, but it could also boil down to other things that are limited. So for example, battery life, things like that. Although we don't typically measure that, but traditionally it's time and it's memory. Okay. Now, when you do analysis, and it's very, very easy to make some broad strokes. This function is slow. This function is fast. Those are not kind of generic descriptions that we actually want to do when we're talking about analysis. That's way too vague. What do you mean by fast? How fast is fast, right? How slow is slow? And we can't really use that kind of description when we're talking about analysis. Those are bad things to do. Like we don't really want to talk about it in terms of that. We want to be more precise than that. Okay. Um, Analysis is also not about a specific number. So if I told you this function takes 6 seconds to run, that has absolutely zero meaning because we never considered, well, how much data is this function processing? How much data are we feeding this? Is 6 seconds reasonable for this amount of data? So if I told you that the function was given like 10 numbers to process and it took 6 seconds, that's a very different statement than 10 million numbers and it took 6 seconds, right? So whenever we talk about analysis, we always have to talk about this relative to something called the data size. So we're always looking at resource consumption given an amount of data. So it's not just like 6 seconds. 6 seconds has no meaning. Okay. If I gave you a teeny tiny piece of data and your process takes 6 seconds to run, well, that's very different than if I gave you like 20 million records and it takes 6 seconds to run. It's very, you have to consider how much data you actually use. So with that said, let's take a look at what we really, really want to talk about in analysis. So let me share this with you. Give me a sec. So when we talk about analysis, most of the time, what we really want to talk about is something called growth rates. And a picture is worth 1,000 words. So what we're really looking at here is just what happens as data grows, okay? So this is found, by the way, these pictures are taken straight from the notes, so the course notes, so you can find these same pictures there. So this first curve that we're looking at is called the constant curve. And what this curve says, and what all these graphs mean, is the following. If we look at this line, this is as the data gets bigger and bigger and bigger. So as my data size increase, how much processing time am I consuming? So you see how this line is completely flat? It doesn't grow, it doesn't move up. So what this means is that as my data gets bigger and bigger and bigger and bigger and bigger, the thing that I'm trying to do doesn't take more resources than before. Okay, so if I have one piece of data, it takes the same amount of time as if it has a million pieces of data. It doesn't matter how much data there is, the amount of time is fixed. And you go, wow, that doesn't seem like something we do, right? But in fact, there are things that you have used that have exactly this sort of profile. So for example, think about array access, okay? So you have an array. If you have 10 elements in the array and you wanted to find the 10th item, it doesn't take you more time to find the 10th item if the array had a million elements in it, right? Getting to the 10th element is a constant cost, okay? So regardless of the size of the array, regardless of how much data is in that array, getting to a specific part of that array takes exactly the same amount of time. It doesn't matter how big the array is. So that's constant, okay? Now, there are other things that are constant. So if you have two numbers, for example, and the number is 5 and 7, relatively small numbers, you add them together, that operation is constant. If you have 2,633, 4,842, and you add them together, that takes the same amount of time, regardless of the fact that those two are very different numbers, right? Now, having said this, there's still only two numbers, so it's different if I have multiple numbers. Okay, so so data size depends on like how you calculate that depends on what you're trying to look at. Okay, so so we'll take a look at some examples as we go. Okay, so that's constant. Okay, things that do not change, and there's actually a lot more. We're going to do data structures later on that actually have this particular like a constant runtime for like inserting, removing, and searching through that data structure on average, constant runtime. Their data structures, they're designed like that. So let's move on. Okay, so this next one is a logarithmic curve. Now you see how this curve starts off looking pretty steep, and you see how it bends towards the kind of bends like becomes more flat. So it's very steep at the beginning, and then as it goes on, it flattens out. It's like it gets flatter and flatter and flatter. And so this particular curve is called the logarithmic curve. Okay, and so what happens here is that in this particular curve, the curve has to use an extra unit of resource for every doubling of the data. Okay, so that's kind of an awkward way to phrase it, but if you think about it, doubling the data when if the original data had one piece of data, doubling it is two. Okay, that's why it's so steep at the beginning, because doubling from one is two. Doubling from two is only four. So you've got like two extra units by the time you got to four, and then doubling that is eight. But if you have to double like 1,000, it's 2,000. If you have to double 1 million, it's 2 million, right? So as time goes on, if I had to double again, so if I need to consume one more unit of resource, my graph would have to extend to about here, right? Like it's a very like it would I would have to double the horizontal axis to gain even one more unit of height. Okay, like this curve would have to be very long for me to show one more growth, right? So because doubling is literally doubling, so doubling here would be all the way out here before it's even 1 unit higher. So that's logarithmic. Now things that have a logarithmic growth rate. So for those of you who have looked at other algorithms, there's a search, very famous search called binary search, right? And you may have studied this already in your course, or you've seen it in other places. Binary search has a logarithmic runtime, okay? Because what happens with binary search is you start out with an array that has n elements in it, and then every time you look at something, you have the array, right? So basically, if you think about it backwards, if you double the data size, right, you make it the array twice as long as it was supposed to be, you would have to search one more time before it turns it into half as what it was, right? So it's that idea. It's this idea that for every doubling of the data, you increase one extra unit of resource consumption. Okay, so this is that's logarithmic. This is linear curve. Linear curve, I know this is not doesn't look curvy at all, right? It's like a straight line. That's what it is, it's a straight line. So the linear curve basically describes what you normally would think is the normal behavior of what happens as your data grows, right? So, if you grow by 1 unit of data, it would take one extra unit of resource. So that's linear. But actually, not everything grows linearly. A lot of things don't. So this is the curve that describes a lot of different things, but certainly not everything. This curve describes, for example, linear search. Linear search has this growth rate. So if you had an array and you had to find something in it, um, then one way to do that is called with something called linear search. And as the array gets bigger and bigger and bigger, you are expected to search more and more and more. And the growth of resource consumption follows this particular straight line curve. This next curve is called log linear, and it isn't. It's kind of. It looks straight over here, right? Like this. If I took a look at just this part, it looks like it's a straight line, but it's actually not. Now you can definitely see more of a distinct curve at the beginning. Now, this particular curve is basically log times linear. So it's the two previous curves multiplied by each other. So if you took a linear curve, right, that would be just a straight line. But for each data point, you're going to multiply log on it. So at the beginning, it's more pronounced because log increases faster as when n is small. But as it gets bigger and bigger, it takes a bigger and bigger n for log to change. And that's why you see it almost like it's flattening out, just like the previous log curve looks like it was trying to bend to a horizontal line, but it never quite gets there. Same thing over here. This next one is the quadrat. Oh, sorry. Um, I should also mention what are the good algorithms that have this curve, right? So algorithms that have this curve include all the good sorting algorithms. Okay, so that would be quicksort, merge sort, heap sort. They all follow this particular curve. Next one is quadratic curve. A quadratic curve it looks like a parabola. It's n squared, like that's why it's called quadratic curve. Okay, so this particular curve is it is basically the curve that describes all the bad sorting algorithms, all the simple sorts. Selection sort, insertion sort, and bubble sort all perform like described by this curve. Okay, so this curve describes the behavior of all the simple sorts. It basically means that for every unit of increase, your data is squared. Okay, so it's n squared. Now, it this will feel pretty slow, and if you actually run some code with this, you will see how this behaves. So this is the n squared curve. This is the cubic curve, so n cubed. I don't think we actually do anything with this particular. We don't have any algorithms presented in the notes that have this behavior. It just means n cubed. And lastly, exponential curve. This particular curve is exponential, which means that it's basically the opposite of logarithmic. So it looks like it starts out really, really, really small, and then it, for some reason, just zooms up like suddenly, unexpectedly, but it's not. Exponential is basically means that for every unit of data growth, your resource consumption doubles. Now, if your resource consumption started at one, then the next unit over is only two. So one and two, who cares, right? Two and four, who cares? It's very slow at the beginning. But as you double and double and double, that increases quite dramatically. So 8 double is only 16. 16 is still a pretty small number, right? But that double is 32. The next one is 64, 128, 256, 512, 1024. And this amount, so every data increase, every data point increase doubles the resource consumption, which is a lot. This describes how like any code that we write, if it is exponential, it basically means that your program is going to be incredibly slow. And even though I said don't use slow to describe your program, it just means that your resource consumption is going to become unmanageable very quickly. Okay, so you can only use something that's exponential for incredibly small data sizes because very quickly you would outstrip the amount of resources that you have. It won't take very much. Okay. So this, to give you an idea of how bad this could get, it's, so I don't know if you've ever heard of this. So if you took a chessboard, okay, like a chessboard, which is 8 by 8, right? And you put a single grain of rice on the first square, then you put 2 grains of rice in the second square, and so on. By the time you try to put rice into the last square, there wouldn't be enough rice in this world to cover that square. Okay, that's how much, like there wouldn't be enough grains of rice for you to fill to 64. So to fill all 64 squares. Okay, and if you want to think about it, even halfway through, 32 squares only. Okay, you're looking at what, 4 billion grains of rice, which doesn't sound like a lot. There's certainly more than 4 billion grains of rice, but 33 squares is 8 billion. Right? It's double, and then double and double and double for every single remaining number. The number gets incredibly big, incredibly fast. So we would have to be aware of how bad this can go. And that's only 64 squares. Okay. So this is how this works. Okay. Um, Anyhow, that's it for this particular video. Thank you.